Hello students, welcome to Smart Engineering Tutorials. Today we are going to see another topic of Unit 2, which is Narrowband FM. In our previous video lecture, we saw that the equation of FM signal we obtained as ST equals to AC cos theta IT, and theta IT was 2 pi FCT plus beta sine 2 pi FMT. And for FM, we saw that the modulation index beta can have two values, and if beta is less than 1 radian, we get the narrowband FM signal, and if beta is greater than 1 radian, then we get the wideband FM signal. So we are going to move this concept further, and we are going to see NBFM and then WBFM. Today we are going to see NBFM. So to obtain NBFM, we are just going to use trigonometric formula of expanding a cos term. So here we have AC cos, and within the bracket we have two parts or two terms. We name them as A and the other as B. So we are going to use the formula, trigonometric formula, cos A plus B, and we know that it is cos A into cos B minus sin A into sin B. So we are going to use it here, and we obtain this equation. We have A as 2 pi FCT and B as beta sine 2 pi FMT. So AC is common, so it will go with both the terms in expansion. So AC cos A is 2 pi FCT, so cos 2 pi FCT, cos A into cos B, cos B is beta sine 2 pi FMT, and then we have a minus sign, cos A cos B minus sin A. This AC is common, will go with both, so sin A is sin A 2 pi FCT and sin B, so sin B is beta sine 2 pi FMT. So this equation, after expanding, we get this full equation. Now we are going to make some approximations, since we are going to study narrowband FM signal, and for this beta value is less than 1 radian. So if the beta is less, or it is, means we are saying it is very minute, very negligible, nearly to 0, since it is very less than 1. So we can see that beta is can be seen inside the angle with two terms, cos and inside bracket beta multiplied by this whole, and the other term is sine and inside bracket beta multiplied by this whole. So we know that the value of angle, minimum value of angle, we can say is 0. So if the angle theta is very small, since beta is very small, so any quantity, any term multiplied by very small quantity will give you another very small quantity. So this whole angle is very small. So if we talk about cos theta, and this theta is nearly 0, is very small, so the whole term will become approximately equal to 1. So cos theta will change to 1. So that's why what we have done, we have approximated cos beta sine 2 pi FMT, which is the term, this one, this is going to be approximated to 1. And if the angle with sine is very small, the approximation in trigonometry we do is sine theta reduces to theta when this theta is very small. We are going to use this in this equation, that with sine, and inside we have beta multiplied with this quantity, beta is very small, so this whole quantity sine theta will be reduced to theta only. So this I have written, beta sine 2 pi FMT will remain. So we are going to make two approximations. In place of this we are going to use 1, and in place of this we are going to use only the angle, that is beta sine 2 pi FMT. So after making these approximations, the equation which reduces to is the first term, that is AC cos 2 pi FCT part will remain the same. So AC cos 2 pi FCT is same, and cos beta sine 2 pi FMT we have replaced it by 1. So I put this 1 here. and minus this second term, it is AC sine 2 pi fct, it will remain. So AC sine 2 pi fct will remain, and the sine term, this will reduce by its angle. So I put beta in the front, so beta sine 2 pi fmt. So this whole equation which we have obtained is the approximate form of the narrowband FM signal. And for this we have taken the modulating signal as AM cos 2 pi fmt. In the previous video we have used this same equation for the message. You can see that video. Now further moving, our next step is to find a block diagram which will generate this narrowband FM signal. So here we are not going to mug up that circuit. We are just going to derive or develop that circuit with the help of this equation. So we will see what we have the terms, what we need, and what we have to obtain from the circuit. The first term is AC cos 2 pi fct. This AC cos 2 pi fct is the carrier. So first of all we'll start with the carrier. I have taken this carrier wave, it is AC cos 2 pi fct. This is the first term. Now we are moving to the second term. In second term we have two terms. I have put this one and this beta along with this as the second term. First term is AC sine 2 pi fct, which is the sine form of the carrier, which is AC cos 2 pi fct. Its sine form is the first term, and the second term is beta sine 2 pi fmt, and the second term is beta sine 2 pi fmt. So first term and second term, we have to obtain these two terms. So this AC sine 2 pi fct can be obtained from the carrier itself. We will pass this carrier AC cos 2 pi fct from a minus 90 degree phase shifter, and this phase shifter will give us AC sine 2 pi fct. So how we have obtained this? This is simple trigonometric thing. See, cos 90 minus theta gives us sine theta, and if I take minus common inside the bracket, cos inside the bracket I have taken minus common, so what will be inside the curly bracket? Theta plus of minus 90 degree. Plus minus is minus, but I have shown plus separately and minus 90 degree. Cos inside the bracket minus common, and we know that cos of minus theta is cos theta. So cos of minus theta minus 90 degree is equals to sine theta. So here basically what I have done is that I have taken minus common, since this and this are the same. So what we can write it as cos, inside I have taken minus common, and the actual we are going to show that theta plus of minus 90 degree is sine theta. It means that we know that cos minus theta is cos theta, so we can write this whole equation as, again, as cos, this minus will have no effect, it will be cos theta, so theta will be theta plus of minus 90 degree, and this is equals to sine theta. So what we have done, AC cos 2 pi fct is passed through a phase shifter, and that too a phase shift of minus 90 degree. So if we pass this cos signal from a phase shifter which provides a minus 90 degree phase shift, it will give a sine theta term. That's what we have obtained here. The simple trigonometry. So this minus 90 degree phase shifter has given us AC sine 2 pi fct, which we needed here, AC sine 2 pi fct. Now the other term which we want is the product of this term with another term which is beta sine 2 pi fmt. So sine 2 pi fmt is how we'll obtain this along with beta. See how we'll obtain this. Since we are using this dashed box shows narrowband phase modulator, I am using the concept of my previous video that we discussed that when we use a phase modulator and with a carrier AC cos 2 pi fct, then to obtain an FM wave from a phase modulator, the input is modulated wave is then passed through an integrator. So the integrated modulating signal is the input to the phase modulator. So we are going to use this concept here. So we have used this modulating signal MT. We have passed this through an integrator, and the integrator output now will be the input to this narrowband phase modulator. So we need product of two terms, this AC sine 2 pi fct and beta sine 2 pi fmt. So this beta sine 2 pi fmt is a result of the integration process. Since in my last video we saw that we obtained this theta it, how? From 2 pi multiplied by integration of fit dt, and fit was the instantaneous frequency and it was fc plus delta f cos 2 pi fmt. So after integration of this frequency to obtain the theta it, what we got at the end, it was 2 pi fct plus beta sine 2 pi fmt. So the integration process, see, we have obtained here beta sine 2 pi fmt. That's it. That is what I have told you, that we get the term due to integration, because we need this term beta sine 2 pi fmt. So this we have obtained from integration, and the integration output is sent into a product modulator, and the another input to the product modulator is AC sine 2 pi fct. So these two terms are multiplied inside the product modulator, and we get this product, this whole product, but this whole product has a sign of minus with it. So the first term was the carrier, it is going with the plus sign. This is the summation, summer, this is going with the plus sign, and the product of these two signals is going along with the minus sign inside the adder, and then at the end of the circuit we get the narrowband FM signal. So this is how we obtain the block diagram from the equation of a narrowband FM signal. Now another point which I would like to discuss here is that we saw that in FM or PM signal, since they are types of angle modulation, the changes which are being made according to the message signal in the carrier is in the angle part, not in the amplitude part. So here the amplitude ideally should be constant, but it is not so actually. Here we have used a sinusoidal modulating signal AM cos 2 pi FMT, we already discussed, and its frequency is FM. Here we have seen that the equation of the FM signal as a whole, if you see, it is like this: cos of inside 2 pi FCT plus beta sine 2 pi FMT. So if we see the angle itself is having a sinusoidal term, and that too with frequency FM. So we say that this equation or the FM signal, and we obtained this narrowband FM by making approximation in that particular equation of FM signal. So we say that the NB FM signal which we have obtained from the modulator above, from the block diagram, here this signal differs from the ideal case in two ways. The first is that ideally the envelope or the amplitude should be constant, but it is not so. The envelope or the amplitude, it contains a residual amplitude modulation. It means the amplitude changes. So there is somewhat of amplitude modulation present in it. And the second is that for the sinusoidal modulating signal, which we have said AM cos 2 pi FMT, we have seen it is AM cos 2 pi FMT. For this modulating signal, the angle theta IT, it contains some harmonics, means it has harmonic distortion of third and higher order harmonics of frequency FM. So these two things are present inside the signal, which should not be present ideally. So one way to rectify these issues is that by restricting the value of beta less than equal to 0.3 radians, these two effects of residual AM and harmonic PM can be made negligible. So now we'll move further. We have obtained the equation, we have obtained the block diagram, and now moving further. This is the equation which we obtained. Carrier AC cos 2 pi FCT minus beta AC sin 2 pi FCT into sin 2 pi FMT. This is the narrowband FM equation. If we try to expand this equation, here this cannot be, so it is like this, AC cos 2 pi FCT. I write it down like this as it is, and here if I see, it is sin C into sin D. If I take this term as C and this term as D, so it is sin C into sin D. So I have written the trigonometric formula which we are going to use here. Sin C into sin D is 1 by 2 cos C minus D minus cos C plus D. So here what I have done, I have taken here C as a frequency FC term. Since this is the carrier and this is the modulating signal MT, suffix M shows modulating or the message signal. So sin 2 pi FMT is the message signal and sin 2 pi FCT is the carrier signal. So we are going to use the formula sin C into sin D. So we have C here and we have D here. So equation will become this. I have written as it is. So what I have done, FC I have taken first and FM afterwards. So it will become, I have a term 1 by 2 and I have cos C minus D with a plus sign and minus with C plus D. So I have done, this is minus here again. We have already a minus in the equation above. So if I write C plus D term beforehand, so minus, since it is with minus cos C plus D, so minus and this minus will become plus. So I put plus here. So and by 2 we have, so beta AC by 2, and now inside we have cos, we are writing the minus term first, so it is cos C plus D. So cos, and I am taking the C, this is whole and this is D whole, so it will become 2 pi FCT plus 2 pi FMT. So I have taken 2 pi T common, so 2 pi T outside and I put only frequencies together. So this is FC plus FM, and the other term, that is C minus D. Now because of this minus, it will come with the minus sign. So minus cos, and inside the bracket again I have taken 2 pi T common and it is C minus D now. So this whole C minus D. So 2 pi T common and inside frequencies is FC minus FM. I have purposely taken FC before so that I can write FC minus FM, because FC is carrier and FC frequency will be higher than the message frequency FM. So I have got this equation after expanding, and now I'm going to compare this equation with the AM equation, that is amplitude modulated wave equation, which we have not studied yet, but we'll study in unit 1. I have written it here directly. AM equation is AC cos 2 pi FCT plus MAC by 2, and inside the bracket again we have the same cos 2 pi T common FC plus FM plus cos 2 pi T common FC minus FM. Now we'll compare these two equations, narrowband FM and AM. The first term, both have the same first term, and NBFM has modulation index beta and AM has modulation index M. And so we have both the things are similar, modulation index into AC upon 2. And inside the bracket if you see, it is cos 2 pi T FC plus FM, both having the same higher frequency FC plus FM. And the only difference is that here we have minus sign, here we have plus sign for the FC minus FM term. Again, same things, cos into 2 pi T common FC minus FM. So if we see that comparing both the equations are the same. The only difference is of sign for FC minus FM term. Now if you want to talk or we discuss about the bandwidth, see, we have the carrier in between. If we try to plot both the AM and FM, it is nearly the same. FC, that is your carrier, and this frequency which is above, that is we have two frequencies. One is FC plus FM, so higher than FC, so we'll say FC plus FM as upper sideband, because it is higher than FC. And the other frequency is FC minus FM, and we call it as LSB, lower sideband, because it is lower than FC. And we are going to plot this. So in the center I've taken FC, at the right hand side, since it is more, so I've written FC plus FM, and left to FC I've written FC minus FM. So it is less, so we call it as lower sideband, and this one is upper sideband. So we try to, if you want to find the bandwidth of this narrowband FM or the amplitude modulated wave, AM wave, both are having nearly the same equation and the same frequencies. So the bandwidth of both will be same. And how we calculate the bandwidth? As upper frequency minus lower frequency. Upper frequency is FC plus FM and lower is FC minus FM. So FC minus FM minus FC minus plus FM. So FC cancel, we get 2 FM. So both narrowband FM and amplitude AM wave both have the same bandwidth. Further, if we want to see the phasor, here we are taking carrier as the reference. So I have drawn here carrier, and to the right we have the USB, that is the upper sideband. Toward the left we have the lower sideband, and if we complete this, we get the resultant of this LSB and USB, and then making the net resultant we get this, and we see that they both are not in same phase. So what we see from the phasor diagram, that is the resultant phasor of narrowband FM is of same amplitude, they are of same length, same magnitude, so but they are out of phase to each other, means resultant is of same amplitude but it is out of phase with respect to the carrier. So that was all for narrowband FM, and in the next video we'll study about wideband FM. Till then, just subscribe to my channel for further notifications. Thank you.